Gaming laws and Aeolian transport.
Good afternoon, everybody. So the topic of my talk will be a bit on the side of the topic of the conference, because I will speak about dilute granular flow and not dense granular flow. So I've been interested in Aeolian sound transport, and I will present some recent experimental work made in wind tunnel. And most of the results I will present have been made by Chuan Ducrot, which is a former PhD student of mine. So, just as a rapid introduction, I just recall you the basic picture we have from the saltation, the sound transport process in air. And it's due to Bagnall, and it dates from the 1940s. And it distinguishes what he called an important mode of transport in air. It's called the saltation process. These are the grains which are accelerated by the wind and bounce over the sun grain. And during the collision, the collision is able to mobilize grain from the bed and to eject it from the bed and to create a small motion called a reptation motion. So at that time, Bagnall has not the same facilities as we can have now. Now we have, due to the improvement of image analysis processing and due to the high-speed camera, we can analyze in very detail the motion of the particle. And here, just a little video to illustrate what we can obtain in a wind tunnel. So we can see the fast grain colliding the sandbed, and you can see here collision, ejection. And so the purpose of experimental work was to investigate in detail the saltation process and to investigate the importance of the boundary condition, and in particular the role of the sandbed, because there is this collision process, this splash process, ejection of particle. And so we want to answer this different question. So we have what we call a saltation layer, where a layer with grain and fluid. And these are the basic questions we want to answer. What sets the height of the saltation layer? Is this layer driven by the wind speed or by another mechanism? What sets the particle velocity, and what sets also the particle concentration? So the strategy we use is to investigate, to come back to a simpler problem and to investigate the particle transport in wind tunnel, but on a rigid bed. It means on a rigid bed where we glued particle on a flat bottom, and we compare the situation with the classical situation in Aeolian transport with an erodible bed. So we have wind tunnel facilities in Nantes, so close to our lab in Rennes. So this is about a 10-meter long wind tunnel, and we can change the nature of the bed. So we choose two types of bed: erodible bed along the whole wind tunnel, and we also use a rigid bed, that is a bed where we glue particles and on the floor. So the control parameters are different in the two situations. In the case of erodible sand bed, so we can feed sand. We can feed the wind tunnel with sand. This is an additional parameter in addition to the airflow that we can tune. So we have two control parameters. In the case of erodible bed, whatever the ingoing sand flux at the enter of the wind tunnel, the outgoing flux is independent of the ingoing sand flux. So in the case of erodible sand bed, the fully developed state of saltation only depend on the airflow because we have an inexhaustible source of sand. So in a case of rigid bed, of course, we have no sand on the floor, so the flow is driven by the incoming sand flux at the beginning of the wind tunnel, and also depends on the flow, on the airflow. So we have two parameters. This is summarized here. So we use sand grain diameter about 0.2 millimeters, and I just recall that for the erodible beds we have a single control parameter which is the shear, what we call the shear velocity, and the shear velocity is related to the basal shear stress through this relation. This is the shear stress squared times the density of air. So we have an order of magnitude of the basal shear stress on the flow. And in case of the rigid bed, we can vary both the wind velocity and the incoming sand flux. So we measure just all the quantity we measure. We can measure the air velocity, the particle velocity, so air velocity with classic method using Peter tube, and particle velocity using particle tracking velocimetry with high-speed camera. And the particle volume fraction is measured just by image analysis and by counting the particle, and rather easy measurement just by collecting the sand at the end of the wind tunnel. We can measure precisely the mass and flux. So I will present you the experimental results. So here, just to start, is a phase diagram in the case of the transport of a rigid bed. So here the two control parameters. This is the incoming sand flux, and this is the air velocity. Here, in fact, actually it is the nominal velocity. This is the velocity at the center of the wind tunnel. So we can fix the incoming flux and look at where the flow is capable to sustain the flow which is prescribed. So for a given incoming flux at high velocity, we have no, what we call transport regime, we have no deposition. And at a critical wind velocity, deposition starts. And this is a very unstable process. And at the end, all the floor of the wind tunnel is covered by sand. So when we can do that for different incoming flux, and we have a transition between the deposition regime and the transition regime. And so for a given velocity, we have a maximum capacity of transport. Above, the flow is not able to sustain the transport, and we have deposition regime. So we can plot the maximum capacity of the flow on a rigid bed as a function of the shear velocity. So this is the open dot here, which evaluates the maximum flux giving the wind velocity, and we compare it to the erodible case here. So you can see that on the rigid bed, the transport is much more efficient because at a given velocity, so we can transport a higher mass flux. So we get through the velocity profile to try to understand why the behavior is different. So we measure first the velocity profile of the particle. So for the two cases, so the field dot refer to the erodible case, and the empty symbol to the field symbol refer to the erodible case, and the empty symbol refer to the rigid bed. So if this is the x-axis, this is the particle velocity, we can see this is a different series from different wind speed, and we can see that in the case on the erodible bed, so the particle velocity is almost unchanged when we increase the wind velocity. So this is quite surprising. And this is in contrast with what happened in the case of rigid bed, when you can see if you increase the wind speed, so you have the first profile here, and then if you increase the velocity and also the slip velocity. So you find different scaling. So if you extrapolate the velocity at the bed, so you find that in the case of the erodible bed, so it's constant, independent of the wind speed. And in case of the rigid bed, so there is a great influence of the wind speed, and you have a linear increase of the slip velocity as a function of the wind speed. And just a summary of the result. Here it is the slip velocity, which is constant in the case of the erodible bed, and it increases linearly with the shear velocity. So we can, other type of results suggest that there is an influence of the air velocity in the case of rigid bed. We can also measure the typical length of the trajectory. And of course, there is a great dispersion of the trajectory, but we can calculate the average mean length of the trajectory. And we get again that in the case of erodible bed, this is rather constant, no influence of the wind speed. And in the case of rigid bed, so it's scaled with the square root, with the velocity square of the shear velocity. And last result concerns the particle velocity profile. So again, the field symbol refer to the erodible bed, and the open symbol to the rigid bed. So you can see first here, in both cases, so this is a semi-log plus profile, that we have an exponential profile. And the exponential profile is defined by two quantities. This is the volume fraction, the extrapolated volume fraction at the base, when v equals 0. And there is the characteristic decreased length of the exponential profile. In the case of erodible bed, so you can see the slope of the exponential decrease, so is independent again of the shear velocity. So the characteristic, this length can be identified as the characteristic height of the saltation length. So it is again independent of the wind velocity. And in contrast, on rigid bed, this is this profile. So you have a much steeper slope, and the slope depends on the shear velocity. And we have a scaling which is the same that the saltation length with the square of the shear velocity. So now let's try to understand these different results and come back to the first analysis made by Bagnall. So using just a very simple argument. So the hypothesis is the following. We replace the distribution of all trajectories by an average trajectory, which has a length ls, this one, and a certain height. So we can define different quantities. We can define the horizontal flux, the mass per unit time and per unit width. And also we can define the vertical flux, the mass per unit surfaces. And we introduce, so two characteristics velocity, the horizontal velocity when the particle rebounds, and the horizontal velocity after when the particle hits again the sand surfaces. So just we can relate easily these two flux, which is related. The horizontal flux and the vertical flux are related by the length of the trajectory. So this is the first relation. So we want to try to have an estimation of the sun flux using basic arguments. And this is the demonstration of a Bagnall. And from a simple analysis of momentum, the particle shear stress at the surface, so I call S grain. This is the small case letter refer to particle, and we'll see that capital letter will refer to the air phase. So the particle shear stress at the surface is just related to the gain of momentum of the particle during the flight times the vertical flux. So the key is to have an estimation of this shear, particle shear. So if we are interested in a fully developed state, so due to mass conservation, momentum, the conservation of momentum, so the total momentum, the grain particle shear stress and the air particle shear stress is constant and is independent of Z. And this the Basel shear it can be written in a function as a function of the shear velocity. So we can use this momentum conservation to have an estimation of the shear stress, particle shear stress at the grain. So we can have this expression, and so which depend on the shear stress, on the saltation length, and also on the particle velocity. How much time I have? Okay. So there's a classical hypothesis to have an order of magnitude of the air shear stress at the base, which is about equal about of the threshold velocities to entrain the particle. And then the Bagnall hypothesis was based just to have an order of magnitude of the saltation length and of the particle velocity, was just based on dimensional arguments. So at this time, it's not the same facilities, and it just assumed that. So now we have seen that is wrong. That in case of erodible bed, the saltation length scale with u square, and the velocity of the particle scale with the shear velocity. And so, if we put this scaling in the relation of the sun flux, we end up with a sun flux which is scaling with the cubic power of u square. And just so this is a classic argument of Bagnall, and this is what we call the Bagnall law. In case of erodible case, we've seen that these quantities, in fact, are independent of the wind velocity, and we end up, in the case of erodible bed, with a different scaling, because these quantities are constant with the wind velocity. We end up with a scaling law which is quadratic with the shear velocity. In contrast, in rigid bed, we've seen these quantities scale with the wind velocity, and we have a cubic law. So I don't have time to develop the argument to explain why with these quantities are independent of the wind velocity, but it is fundamentally due to the property of the splash process. And so I have not the time to develop. I am too long. So I will just conclude. And so with different, we studied two different situations, erodible bed and rigid bed. In a rigid bed, the transport is much more efficient. And the property of the saltation layer is mainly driven by the wind strength. In the case of the erodible bed, the saltation layer and all the saltation length and particle velocity are controlled by the splash process, which fixes the velocity of the wind, and this quantity are invariant with the wind strength. And so within this example, this This illustrates, in a case of sound transport, the importance of the boundary condition. And in an audible bed or rigid bed, you have a completely different dynamic of transport. Thank you for your attention.
The next speaker could come up and start making the transition, and we could take one or two quick questions during that time. Any questions? All right, well, let's go ahead and thank our speaker again.